We throw around words like work, energy, and power every single day. But what do they actually mean in the world of science? Well, it's not always what you think. Let's dig in. Okay, let's start with a real head scratcher. Picture this. You've been studying for hours, your brain is fried. Or maybe you're pushing against a brick wall with all your might, muscles screaming. Feels like a ton of work, right? Well, what if I told you that in the eyes of physics, you've done zero work? Absolutely none. How can that be? That's the puzzle we're going to solve. And right here, this is where the confusion really kicks in. So on one side, you've got stuff that feels like work, pushing that unmoving rock, holding a super heavy box. But on the other side, you have what science actually calls work, lifting a book, pulling a little toy car. They seem so different. So what's the secret ingredient that makes one work and the other not? All right, to crack this case, we have to get on the same page as the scientists. We need to nail down their super specific definition of work. And here it is. It all comes down to two non-negotiable conditions. First, you gotta have a force, a push or a pull. Simple enough. But here's the kicker, the second condition. The object has to move. It has to be displaced. If it doesn't budge, I don't care how hard you push, scientifically speaking, no work has been done. Both boxes have to be checked. End of story. And of course, there's a neat little formula for this. Work equals force times distance. Think back to that wall. You're applying a force, for sure, but the distance the wall moves is zero. And anything times zero is, well, zero. Zero work. But lift that book, now you've got a force and you've got distance. Boom, that's work. So how do we measure all of this work? We use a unit called the joule. So what's a joule? Imagine lifting a small apple, which takes about 1 Newton of force. If you lift it 1 meter off the ground, you've just done 1 joule of work. See? Now we have a real-world way to measure it. Okay, so we know what work is, but what gives us the ability to do work in the first place? Where does that oomph come from? Well, that leads us straight to our next big idea, energy. In the world of physics, energy is just the capacity to do work. That's it. Think of it like this. Energy is the money in your bank account. Work is what you buy with it. If you have energy, you have the potential to make something move. It's the currency of the universe for getting things done. Now, this energy currency comes in a couple of main flavors. First, you've got kinetic energy. This is the energy of doing. It's energy in motion, a speeding car, a falling coconut. It's happening right now. Then you've got its counterpart, potential energy. This is the energy of waiting. It's stored up, ready to go. Think of a stretched slingshot or a boulder teetering on a cliff edge. The potential is there, just waiting for the right moment. And yeah, you guessed it, we've got formulas for these too. For kinetic energy, it's all about mass and speed. But look closely, the velocity is squared. That's huge. It means if you double your car's speed, you don't just double its energy, you quadruple it. And for gravitational potential energy, it's simpler, just mass, gravity, and height. The higher you lift something, the more potential energy it stores. Okay, this next part is kind of mind-blowing. We've talked about these different types of energy, but it turns out they're all connected by one of the most unbreakable rules in all of physics. It's called the law of conservation of energy, and this is a biggie. It says energy can only be converted from one form to another. It can neither be created nor destroyed. Think about that. You can't just make energy out of thin air, and you can't make it disappear, ever. So what does that really mean? It means in any closed system, the total amount of energy is always the same. It just changes hats. Remember our kinetic and potential energy? It's like having two pockets. You can move money from your left pocket to your right, but the total amount of money you have on you doesn't change. Let's make this super clear with a falling ball. Imagine holding it at the very top, just before you let go. It's not moving, right? So its kinetic energy is zero. All of its energy is potential, stored up because of its height. 100% potential. Okay, now we drop it. As it falls, it picks up speed. Right at the halfway point, it's lost half its height, so it's lost half its potential energy. But did that energy just vanish? No way. It transformed into kinetic energy. So now it's a perfect split. 50% potential, 50% kinetic. The total is still the same. And what about right before it smacks into the ground? Its height is practically zero, so its potential energy is pretty much all gone. And where did it go? You got it. It's been almost completely converted into kinetic energy. The ball is moving at its fastest right here. The energy just changed its form from 100% stored to 100% motion. So we've got work, and we've got the energy to do the work. But there's one last ingredient we haven't talked about: time. How fast does this all happen? And that, my friends, is where power comes in. So let me ask you this. Say you have two people, and they both do the exact same amount of work. Does that make them equally powerful? Let's say they both climb an 8-meter rope. Same weight, same distance, so the work done is identical. But one zips up, and the other takes their sweet time. What do you think? Well, the numbers don't lie. Look at this. Both climbers do exactly 3,200 joules of work, but girl A does it in a blazing 20 seconds. Girl B takes 50 seconds. Because girl A did the same work in less than half the time, her power output is way, way higher, 160 watts versus a mere 64. So the answer is a big no. They are not equally powerful. And that's precisely what power is. It's not just that you do work, it's how fast you do it. Power is the rate of doing work, or the rate of transferring energy. The formula for it is as simple as it gets. Power equals work divided by time. It's all about how much work you can pack into each second. And the unit we use for power is the watt. And it connects everything so perfectly. 1 watt is literally 1 joule of work being done every single second. It's the perfect marriage of work and time. So let's recap. Pushing a wall till you're blue in the face, not work. Lifting a tiny book, that's work. We learned energy can't be created or destroyed, it just changes costumes. And power? Power isn't about raw strength, it's about speed. So now, with this new scientific lens, look around you. A car accelerating from a stoplight, a bird taking flight. It's all a beautiful dance of work, energy, and power. The question is, how does knowing the rules of the dance change the way you see the world?